We're good? All right. This is take two, Drew. We were messed up last time. So you tried some examples of sketching galvanic cells. You had to determine what the electrodes should be. You had to determine what the cell potential was given the table. I imagine that there were some questions. So I'd like to go at the beginning of the hour through some of the process involved with it. I would expect the line notation was challenging for you. Line notation is confusing. So we're going to talk about that too. In fact, let's do line notation first so that I can get to this more difficult example and show you after you've at least seen and maybe understood that. Spencer, let's go 2 slides before. Yeah. This is a much more simple chemical reaction where you have aluminum ions and magnesium, the metal, reacting. This is a spontaneous reaction. The magnesium oxidizes. Magnesium is very good at oxidizing. You can tell from that table that I've given you. That table, by the way, you'll keep. And then aluminum is pretty good at reducing. No, it's not actually good at reducing, but in this case it does reduce because the magnesium is so willing to oxidize. Now, are we all good with what the anode and the cathode are? Anode oxidation occurs there. The cathode is where the reduction occurs. Determine the cell potential. Are we pretty good at this?
Sure.
You find the oxidation potential of magnesium. On that table, it's going to be the reverse, but then you've got to turn it around. Change the sign on it. And then the oxidation, or the reduction of the aluminum ion. Add those two together. You must get an answer that is what? Positive. If it's not positive, it doesn't happen. And you'll have no flow of electrons. Express the cell with line notation. Here's what we do with the line notation. You're going to have, in the first case, Spencer, no, let's not. Huh? Not, you always will express line notation. With the anode on the left. Now I told you with the sketch, it doesn't really matter what beaker you make what. You could make the anode on the right and then the cathode on the left and have the electrons going that way. The electrons always go from the anode to the cathode, always. Why? Because an anode oxidation occurs, and the oxidation is the loss of electrons. So the electrons are leaving the anode and going into the cathode.
Is the line notation basically just what we draw except in lines?
Kind of. It is kind of what you draw, but specifically what goes on one side of the line matters. It makes a difference. Thanks a lot for burning that thing too, by the way. Everybody's enjoying the smell of it.
For the gold, for the galvanic cell inside each do we put the after the reaction or during or before the reaction?
In the line notation?
Yeah.
Both.
Both?
Yep, both of them go in there.
Oh,
both the reactants and the products have to show up in the line notation.
Wait, so how do we show that?
Well, that's what I'm trying to show you.
Oh, yeah, okay, sure.
Okay, now this is what's happening at the anode. This single line separates physical states. The electrode in this side was the magnesium reactant, and then it changes into magnesium ion. So that single line separates the two physical states. The outside of it always has the electrode. And then that's what the product of that reaction, that half reaction was, because at the anode only a half of the reaction is occurring. Over here on this side, we had aluminum ion reducing to aluminum metal. Now the aluminum metal was the electrode over on this side. You have to have a metal electrode.
Electrode. It's a Pokemon.
Really? Is that what we're talking about? This double line represents the salt bridge. That's what's separating the anode from the cathode. You'll always have the double line in the middle. Now, the notation for the single lines isn't as obvious. And what I need you to know for right now is the single line separates the physical states. It's always a solid electrode. And then on the inside there, between that line and the double line, is going to be the aqueous reactants and or products. Because you may wind up with reactants in there. We're going to see that in the next example. But this is what the line notation will look like. So it's describing what's happening. It's not really describing the reaction, the chemical equation so much. It's kind of more describing the sketch that you made, but with this kind of notation. It's a short way. Electrochemists will just jot down what reactions they're using like this. Spencer, let's move on. This is the sketch of the cell, and you see that I have the same cell line notation there. One more. Okay, now this one was a little bit more complicated. You were able, apparently, the sub tells me, to get through this one. Yes?
Yes.
But not really, you didn't understand it?
No, we didn't really understand.
Okay.
We're like, what is...
So here's what it tells us. We need to make a sketch. So once again, you're going to draw 2 beakers with the salt bridge. You need to identify what is oxidizing and what's reducing here. Now what I've given you are 2 reductions. Because in both of these, electrons are in the reactant side. They're both taking in electrons, right? So they're gaining electrons, reduction. These are both taken off from the table, the reduction potentials. One of these needs to be turned around to make an oxidation, though. These two, the way they're written, cannot work together. Because if something takes in electrons, something else has to give off electrons. You with that?
Yeah.
Which one gets turned around?
The first one.
Yes, how do you know? This plus this must be a positive number when you add them together. And remember, the one that you turn around becomes negative. So when you have 2 positives and one needs to be turned around, use the smaller positive one to turn it around. And that's the top one. So we'll turn that top one around. It's going to give us a small difference there. Well, a small sum between those two. But yeah, that's what's going to happen. So this MnO4 winds up being in the oxidation. So it's going to be, I'm going to erase this. The oxidation is going to be Mn plus 2 plus the 2 waters yields, so strange, not 2 waters, 4 waters. So strange to just write a single direction arrow. After all this equilibrium we've done, makes permanganate and 8 hydrogens and 5 electrons. Okay. So, and then this thing has an oxidation potential of negative 1.51. Yeah? That means that this reaction does not really like to occur if it has a negative potential. Do you remember back in chapter 4, earlier in the year, we saw permanganate a lot. It's very common for reducing. It's pretty unstable the way it is. That's why when you turn this thing around, it's got a negative 1.51 oxidation potential. That is not favorable. Things like to have a positive oxidation potential. You really made the room smell. Who was it that burned that goldfish?
Tarun.
Was that you? Ooh, man. Is anybody else offended by that smell?
Yeah.
I don't know if it's...
What
Man,
smell?
it's terrible.
I'm too sick to smell anything.
Oh, good. What?
I don't know if it's...
Ah, it can't be just a
I
cot.
think it's...
It's not. I'm actually mad at my mom right now.
Cotton doesn't have a smell when you burn it. I tried it at home.
Is that what you're eating? Oh my gosh, those smell terrible. Please hurry up and eat those. Finish. Oh my gosh, it's terrible.
Something smells.
Burning?
Nasty? I don't know.
It does smell nasty.
I smell
Thanks
burning.
for saying that, because it tastes like Indian food. That's probably why you're saying that.
I don't like this smell.
Same thing.
Professional chef.
Hey, listen to the apron. It's bad. Okay. So, now tell me this. Well, let's go ahead to the next slide. We'll come back to the line notation, because I don't think I ever even asked you to do the line notation for this. This was the sketch of the cell. In this case, both in the anode and the cathode, you had one ion changing into another ion. So when that happens, we just use platinum electrodes. We had the Mn plus 2 changing into MnO4 negative. That's an ion changing to an ion. So in that case, we do not use manganese as the electrode. You just use platinum. Remember there were 2 things that were good about platinum?
Inert.
It doesn't.
It's expensive.
It's inert, does not react well. The cost of it doesn't matter for this. I guess it does because we can't use it.
Wait, so what is
The
that poor
conductor,
man's
right.
platinum?
I can't tell you right now. I'll tell you later. Don't want to have it recorded. It's embarrassing.
Wait, so what are we gonna use instead of it?
I'm not telling yet.
He just said that.
We can use something besides platinum. That'll work fine. In the cathode side, we have the IO4 negative. This is per iodate, changing into IO3 negative, just the iodate ion. Again, we have an ion changing to an ion, so that's going to have platinum electrode too. Does everybody feel comfortable with the whole purpose of using a salt bridge?
Yeah.
Why do we have a salt bridge? Because the salt bridge has a dissolved salt in it. It's sodium chloride, it's potassium nitrate, it's something that's dissolved that has a lot of ions. As the electrons go that way, as the circuit has a current flowing, this thing is becoming more positive because it's losing all these negative particles. So a positive charge builds up in here. But in science, in real life, you can't build up charge. So if positive charge is building up, then the negative ions from the salt bridge migrate in there. Nature knows it can't be charged. So the negatives flow into here. This is gaining electrons, so we're gaining negative charge here. Positives will flow into here from the salt bridge. Jordan?
Is there actually something inside the salt bridge?
Yeah, it's got to be like dissolved salt,
Oh.
where you got positives and negative ions. Those ions are what will migrate. Yeah, fruit?
Can run out of those ions?
Yes, and then the circuit stops.
Okay, so it doesn't,
I don't think it's possible like that the IO3 can go through the salt bridge. I don't think that, it might happen. When the salt bridge is depleted of its ions, they may start to migrate all the way from here. Excuse me, into there.
Wait, in order for that to happen, then we have to like cup our hands to.
To get it to turn over, yeah, you gotta put your hands over it. I'd wear gloves if it was me. Because this stuff, like you got strong acid in there, you don't want it. All right, now here's something that I need to make very clear. Taking a look at this table that I gave you, standard potential, reduction potential. Eric's got a big stack on his desk.
Oh, sorry.
Well, I see you have one. You're the reason I have to make one for everybody, because I can't keep a class set.
nice job.
There's many of you, Jessica, so that's okay. See how it says standard reduction potentials? That standard is important.
1 APM.
Yes, for gases, you have to have 1 atmospheric pressure. For solutions, what was the standard?
1 mole.
1 molarity. Now, here's what's weird. When it says standard, that means the reactants and the products that are solutions must be 1 molarity. So that means if I'm going to make this cell at standard conditions, I'm going to have 1 molarity of the Mn plus 2. That's a reactant. But I also have to have 1 molarity of permanganate.
That's very specific.
So we need to start with already 1 molarity of the product. You don't start with 0 product like we're used to doing. You start and 1 molarity of hydrogen ions. So you have to have 1 molarity of every ion that's in the setup. And that's the same thing as over here, reactants and products. Now once the current starts to flow and the electrons are going over there, what happens to the concentrations of everything? Changes. The manganese is a reactant. So as the current flows, this is concentration is going to go down because it's going to be used up. This concentration is going to go up. So as soon as the circuit starts, like flowing electrons, you're going to not be at standard conditions anymore. So this is only good for like a brief moment in time. Why do we have it then? Well, if your concentrations are not at 1 molarity, you can find out what the cell potential would be as well. I warned you about this thing called the Nernst Equation. Remember we talked about that 2 days ago? The Nernst Equation accounts for when your concentrations are not 1 molarity.
Does
So
Nurse
we'll
have
see
a
that
funky
later.
haircut?
I don't know what Nernst look like. It'd be interesting to see too. Anybody want to look up Nernst?
I got it,
The
I got
picture
it.
of Nernst?